So what we're going to do in today's lecture is to take a concept from mathematics, and we're going to analyze this concept from the point of view of category theory. What that means is that we're going to, first of all, describe it in the language of category theory. And then that will help us see where does it fit with the rest of ideas in category theory, and also in relation to other areas of mathematics. And the concept we're going to look at was suggested by Alexandra here. It is that of a topological group. But let me begin with a specific example of a topological group, which is the real numbers. So we want to think of the real numbers as a group under addition. However, real numbers also has other structure. There is multiplication, for instance, and so on. But what I want to put there is the topology. So you see there is a bit of, we keep information a bit of on the algebraic side and also on the geometric side, and we put it together. Now, it is not just that there is addition defined on the real line and there is topology on the real line. Also, these two structures interact with each other. Specifically, addition is continuous. And not only that. So what is addition? Addition is a binary operation. So we can write it as a function from r plus r to r. But because it's a group, there is also the operation of inverse. So there is another map from r to r, which takes an element of the set and assigns to it another element called minus x. There is a third operation involved here, although one doesn't usually think of it as an operation. It is choosing the identity element of this group structure, which would now be from a singleton set. So this would be a function from a singleton set to R. It maps.
So I heard like seen something like in general algebra, and they usually take, I think, empty set instead of one element singleton. No?
That doesn't matter. You mean instead of, are you saying that this whole thing should be empty set?
I think they usually choose element using some empty set, and call it a nullary operation.
Okay, so are you talking about the star being the empty set?
Yep. No. The whole thing is empty set.
If the whole thing is the empty set,
yep,
there is a problem, because then there is only one function from empty set to any other set. And that function will not do anything. It will be just the empty set of our pairs. Right. We want the function to select an element of R. So we definitely need something inside the singleton. And if I'm using axiomatic set theory, it's indeed most convenient to put empty set here, because that's the first set we know exists. Now, there is a pattern to these maps. Specifically, there's a pattern in their domains. The domain of plus is r squared. The domain of minus is r to the power 1. And the domain of the identity element, who would like to tell me what it is?
Oh, 0.
Did you say r to the power 0?
Wait, what was the question again?
How can we represent this object in a similar way as we did the others? So r is r to the power 1, R times R is R squared. What about this one? But I gave the answer already. So we can think of the singleton as R to the power 0.
Yeah.
And because of this, we say that plus is a binary operation. Minus is unary. And 0 is nullary. Of course, there are some axioms that these operations must satisfy. The axioms of a group are associativity, the axiom that defines what minus does, which is, well, maybe I should first write down the axiom for 0. X plus 0 equals x equals 0 plus x. And then the third axiom will be the one that describes the function of minus. X plus minus x equals 0 equals minus x plus x. Now, this list of axioms is not the most efficient one. We can discard some of these equalities here, and because they follow from the others. In fact, you can even have a single axiom defining a group structure using just a binary minus operation. There is a paper about this written in the 1930s. It's a very interesting paper. And you got a very long single axiom that captures all of these equations. And it's not easy to prove. All right. Now this part is the group part, right? This is what makes R into a group. We also have the topology here, tau. So let's write what that means. Tau is a subset of the power set of R. And as you probably know, there are 3 axioms. The first one says that the empty set and the entire R is in tau. Second one says that for any 2 things in tau, their intersection is in tau. And the third one says that for any set of subsets of R that are in tau, so for any subset S of tau, the union of S is also in tau. And again, there is a redundancy in this list of axioms. I could take S to be the empty set, then the union of S would be the empty set. And so I don't need to say explicitly empty set is there. Also, in the second one, if I replace binary closure under binary meets with closure under finite meets, but now I'm talking about meets in the lattice, in this lattice. Otherwise, if I talk about intersection, that's not going to work. Because empty meet is going to be the top element of the lattice, but empty intersection doesn't exist. Anyway, so these are the 3 axioms for topology. So this is what makes topology. And we now want to add some axioms that link the 2 structures with each other. And that is simply the fact that plus is continuous. Plus is continuous. But I don't think that's enough. I think we also need to require separately that minus is continuous. Otherwise, it will not work. Well, we haven't defined what a continuous function is. It's a function such that inverse image of every open set is open. there is a natural way of turning this into topology. You can have Cartesian product of any two topologies to the topological space. In fact, that will be the product of objects in the category of topological spaces. It's clear what it means for this to be continuous. And the third map, we're not going to write it out. Well, maybe we should for now, but it actually will automatically be continuous because r to the power 0 is a singleton topological space. Everything there is open. And so this map, whatever it is always going to be continuous. Again, there are some redundancies here. Now, if I look at it, okay, first of all, it's very important that we know that class is continuous. In analytical mathematics, it plays a huge role. But now if I zoom out and I ask myself, what's going on here? We're taking two different kinds of structures and putting them together in a certain way. Is there a general process of putting structures together? And it turns out there is one. But maybe those who haven't seen that lecture that you have seen, Alexander, can come up with an idea of how we could extract from this a general method of putting two structures together. Do you see any categories anywhere here on the board?
I mean, we have the category of groups and topological spaces. Not on the board, but I mean.
Yeah, so we have two categories that could be useful here. One is the category of topological spaces, and the other is the category of groups. And the first one, morphisms are continuous maps. And the second one, morphisms are just group homomorphisms, those that preserve the operations. Okay, but what do we do next? Is there a way to glue these two categories together somehow to get now the category of topological groups? That's what a topological group is when we put all the axiom set aside here.
Well, first it looks like we just force the objects to coincide. So just...
Okay, so Carlisle is suggesting to take the, you mean the underlined sets probably, right?
Yeah, yeah.
Carlisle is suggesting something interesting. You're suggesting to take the pullback of the forgetful functors.
Yes, definitely.
Yes. So we've got the category of topological spaces, we've got the category of groups, and we've got the category of sets, and there are functors going from each of these categories to the category of sets. What do these functors do? They forget the structure. They just keep the underlying set. For a group, I'm writing group with a plus only because 0 and minus can be determined by plus, but usually in algebra, but at least in abstract algebra, it's not a good practice to do that. You would want to list all the operations, not just one of them. So we forget the group structure, we are left with just G. Now, those of you who remember how pullbacks work in the category of sets, they work in a similar way in the category of categories. You would take pairs of objects, one from here, one from there, which map to the same place here. But mapping to the same place means they have the same underlying set. So this pullback over the category of sets, in this pullback, objects that live there will indeed be of the form that we're interested in. So it will be a set equipped with topology, and then the same set equipped with a group structure. Okay. what this achieves so far is just to have a structure like this, satisfying two sets of axioms, the group axioms and the topology axioms. We do not get these out of that pullback construction, the thing that links the two structures. So any further suggestions? What do we do after that? How can we isolate?
So is it like that easy, or it's not all that we have to do yet?
Sorry, I didn't catch that. Can you repeat, please?
So is it a whole construction, or we miss something out?
Where?
So when we construct this pullback, so will it respect our operations? I mean, topology and this growth.
It will not. It will not. That's what I said. So the operations. Yeah. So that's exactly what I said. So these will not be continuous. That's what you're asking, right?
Yep, exactly.
Yeah. No, I agree with you that we're missing those. The question is how to get them. Let me actually put this on the other side. So we now can kind of realize that perhaps topological groups live inside that bigger category. The morphisms will be defined indeed the same way as here, because a morphism of topological groups is a function that's both continuous and also preserves the group structure. And that will be achieved through this pullback construction. Just like objects, also the morphisms are defined in such a way that they map to the same place here, which means that as a function between underlying sets, they're the same function here. So how can we separate this from this bigger pullback category in such a way that we now have exactly these three conditions hold? Any suggestions there?
So maybe we'll write like some diagrams and say that they commute, and therefore.
Yeah, but that was cheating, Alexander, because you already saw the definition.
Yeah.
You've seen the definition before, so I was asking either from where we are now or someone who hasn't seen the definition. So the thing is that we want to say that plus is continuous, but plus we never see plus. Plus is something that's inside specific objects in this category. When we apply the forgetful functor, it gets removed. So we will never be able to look at the plus and view it from the context of topological spaces. So we're kind of stuck here indefinitely. And then it turns out that what we need to do, instead of thinking of it as living inside the pullback, which is a very symmetric way of thinking about it, because these two are very symmetric, right? We're going to have the same pullback if I swap the roles around. However, these axioms are highly non-symmetric. I'm saying that the group structure maps are topological morphisms. I wouldn't be able to say the opposite. What would it mean for the topological structure to be a group homomorphism? I don't even know how to say it. Yeah. So this definition is highly non-symmetric, and we need to take that into account. In fact, it's an open problem in category theory to make it into symmetric one.
To make this definition.
Yeah, so we're going to now explain what a topological group is from the point of view of category theory, but it will force some kind of ordering what we do first. And the open question is whether there is a way to do it the other way around.
And that's open, it's not.
It's open because existing categorical structures do not tell you what to do. So you need to invent some other way of interpreting what does it mean to do the other way around.
Yeah.
So you first have to come up with what it means to do the other. Even that is not possible.
Yeah.
Like here, what does it mean that topology preserves group operations? We don't know.
Can I just
Yeah.
so in a topological group, do you always have the homomorphisms are continuous as well?
You mean when you have a morphism of topological groups?
Yeah.
Yeah, every morphism of topological groups is required to be both a group homomorphism and a continuous function, which is something we can already get from the pullback if we knew how to identify the objects. So the non-symmetric construction we're going to perform now is the following. I actually want to make use of the 6 boards that we have here. So instead of erasing anything, I'm going to, I hope you don't mind, Brandon and Alexandra, I'm going to give you another seat here in the room. I'm going to move the camera. We move there, or maybe there is better. Brandon, you probably haven't seen these boards, have you?
No, I don't know which room this is.
1006. Bruce arranged for these nice boards here.
Oh, upgrades. Excellent.
Okay, so when we say that those 3 maps are continuous, we're basically saying that they are morphisms in the category of topological spaces, aren't we? Because morphisms in the category of topological spaces are continuous maps. So the same for the other 2. So this is a morphism in the category of topological spaces, and also this one. So we can view a topological group as an object in the category of topological spaces that is equipped with 3 morphisms plus minus 0 that satisfy some axioms, namely group axioms. And then we get a topological group. The fact that these are morphisms in the category of topological spaces is what takes care of continuity of the 3 maps. But the whole point of doing this is to be able to do something similar for a general category, not just for the category of topological groups. So how can we define the idea of having 3 morphisms? First of all, we need to be able to express these constructions, the ones that define domains of these morphisms in a general category. And then secondly, express group theoretic axioms in the categorical language. What if we replace top with the category, sorry, with a general category? All right.
So are we now thinking of just replacing top, not group?
That's right. We're just going to replace top, and we're still going to keep the groups. But now these will be groups inside another category.
Yeah.
And that's the asymmetry of the construction.
So can you please repeat what you exactly mean by symmetry and asymmetry here?
We prioritize topological spaces as being more fundamental structure. And then we viewed the group structure as something living, as morphisms living in the category of topological spaces.
So we build up this on this ground, yeah, of topology. Oh, okay.
Yeah. Had we chosen to do the other way around, we would have said, okay, let's take the category of groups, and now we need to define what it means to have a topology as some kind of morphism in this category. And we have no idea about how to do that. This part of the structure is easy. These constructions are easy. They are finite products. Right? This is binary products, unary product, and empty product.
Yeah.
So n equals 2, 1, and then 0. So we don't have a problem dealing with this part. But what about the group axioms? So let's write them out one by one, and as some category theorists like to say, categorify the axioms. So let's look at the associativity axiom. X plus 1, y plus z equals x plus y plus z. Can we turn this, which is an equation inside R, but now R is a set, and so we can talk about its elements. We now want to talk about this equation without knowing that R is a set. We just know that R is some object in an abstract category. So we want to switch from elements to arrows. And of course, one way to do this is to use generalized elements. And we already developed the theory of generalized elements. So we could take a fixed space C and think of X, Y, and Z to be arrows from C to R. And then I can start forming these constructions. For if I take R cross R, by the universal property of the product, I'm going to have the pair XY, right? The one that's induced by X and Y into the first R and the second R. And then I can compose that with plus. So this is how we can operate on generalized elements. What we get here, the composite of plus with the pair XY, is something we can write as X plus Y. So we managed to build this term. Let's build the bigger one. But now we just think of this as a generalized element itself and do the same construction with that and Z. So now we have induced map into, again, R cross R. The first one here is X plus Y. And the second one is Z. And again, we can compose it with plus. Whatever we'll get here, we can call that X plus Y plus Z. We've built the entire term. The same way we can build the term on the right-hand side of the equality, we can require they're equal. And now we could say, okay, this is easy. We can do it, let's move on. But we're actually going to be able to simplify this. So we're not going to skip the details here. Let's do it all the way. So we now have two morphisms from C to R. One of them is x plus y plus z. The other one is x plus y plus z. And we want them to be equal to each other. And this is for every base C and every three generalized elements x, y, z with base C, so elements of COM CR. I'm still using the bold phase R, but now we just think of this R as an abstract object in an abstract category having products. There must be an advantage doing things in a categorical way. When we do things set theoretical way, we have to say for every x, every y, every z. If this equality holds just for one specific value of x, y, or z, it's not enough. We will never be able to find a specific x, y, z for which this holds, and that ensures that it holds for every other, not in a general group. But it turns out that with generalized elements, we can do that. And this is actually one of these nice things about generalized elements. Because remember, well, initially, it felt like we brought in an additional parameter, C. So we made things even more complicated than in set theory. But now, in set theory, C is always a singleton. We will now choose a different C that's not a singleton, which will allow us to consider fixed x, y, z, for which this equality will imply every other such equality for every C and for every x, y, z. Isn't that nice?
Yeah. I'm still suspicious time to see it.
So Carlyle says he doesn't believe that's possible. For every, well, for conditions like these, which are expressible in the language of generalized elements, one can almost always build such specific instance of the values of the parameters. And in this case, that should be simply R cross R cross R. Triple product of R. And the generalized elements we're going to fix will be, can anyone guess what they will be? We now want three morphisms from R cubed to R. And in category theory, when you're looking for a morphism, you don't look for it. You just pick the one you have by definition of.
Will it be like just projections?
Yes. Pi 1, pi 2, and pi 3. And now let's write down what it means for these two to be equal when x, y, z are pi 1, pi 2, pi 3. So we've got R cubed here. We've got R. We've got pi 1 plus pi 2 plus pi 3. And we've got here pi 1 plus pi 2 plus pi 3. We're requiring they're equal. And now we're claiming that this will imply that they're equal for every C. Well, in the category of topological spaces, it's already clear that we capture what we wanted. Because what are elements of x cubed? They're triples x, y, z, right? What do these maps do to that element? The first map. So what does pi 1 plus pi 2 do? It projects on x, projects on y, and then adds them. So the first map gets mapped to x plus y plus z. Second one gets mapped to x plus y plus z. Yeah. And so if they're equal, then these are always equal. But we can still do the same thing in a general category by thinking of this as a generalized element itself. And then we will be able to lift this problem to that problem, reduce this problem to that one. So the same thing that I drew before, I could have drawn in a different way, where instead of C, I would have had singleton, but now I'm going to use a general C. And arrow to product, to cube, will be a triple of generalized elements. And then one can check that when I compose this with that, I will actually get exactly that morphism, x plus y plus z. And when I compose this with that, I will actually get I1 plus I2 plus I3. And so, if these two are equal, they will remain equal. I'm composing with this one. Yeah, I meant to say here, sorry, I meant to say here x1 plus y plus z. Thank you. X plus y plus z. So if these two are equal, by composing it with that one, we'll get two maps that remain to be equal. Let's get convinced of that. Let's at least check that this triple composed with that is going to give me exactly this. So I go from C to R cubed by x, y, z. Then I take pi1 plus pi2 plus pi3. Okay, but there is something wrong with writing this down. Wait, is there? Sorry. No, there's nothing wrong there. So how do we form this arrow? Let's just recall that. So we form this arrow by going first to R cross R, and then doing plus, right? And we go to R cross R by pi1 plus pi2, comma pi3. Can you see online that what I'm writing here is not too small?
No, it's all right.
So this morphism decomposes that way. Maybe I'm going to decompose it downwards so that there is space to expand further. Pi1 plus pi2, comma pi3. Okay, now I need to calculate this composite, right? It must be a pair. In the universal property of a product, this middle map, which we can call Fg, when it's induced by F and G, they satisfy this commutativity, right, of the diagram. So I've got some morphism going to R cube. No, let's put R cube now here. And then I've got the two maps. In this case, F is pi1 plus pi2 and G is pi3. And I've got some morphism going into R cube from C. This composite is the one I want to compute. That's this composite. But don't you agree that this composite will be induced morphism into the product by universal property using this composite and that composite? Wouldn't this composite be the unique map that makes these triangles, the extended triangles here, commutative? Because it's already there, and then it must be D1. What I'm trying to say there is that if I want to compose Fg with H, that will equal F composed with H, G composed with H. The map, the morphism that's induced by F composed with H and G composed with. Is this clear for everyone, or maybe we should go into detail there. Brandon, is that clear?
Could you repeat the last part?
Okay, so I'm now kind of developing a rule how to compose a morphism with another one where the other morphism is induced morphism into product. So it's an ordered pair, FG. How can we compose it with H? So that composite will be a morphism from C to R squared, right? And if I compose that with pi1, it will be exactly HF, right? Compose it with pi2, it will be exactly HG. So that's what I wrote here. FH, GH. This composite will then be the unique morphism that makes that is induced by FH and GH. That's what I said. Is that's clear, Alexander?
Yep.
So I just have to bring this triple inside each of these components, compose with them. And when I bring it in for pi3, it will be just composing this with pi3, which will be Z. What happens when I bring it in here? So I still need to work that out. So what is going to be pi1 plus pi2 composed with XYZ. Well, recall that this morphism, pi1 plus pi2, is plus composed with pi1, pi2, composed with, and then we have the third one also, right? So this one decomposes like that. And that comes from here. That's how we define this expression x plus y. It's the pair xy composed with plus. Are you okay with that, Brendan?
I think so, yes.
So pi1 plus pi2 decomposes as plus composed with pi1, pi2. And then I use the same rule as I introduced there with FGH. I can bring this triple inside each coordinates. I'll get plus composed with pi1 composed with a triple, but that's x. And then pi2 composed with a triple, which is y. Because pi1 picks out the first coordinate and pi2 picks out the second coordinate. And so then this ends up being x plus y. So what I have here is x plus y.
The domains, or confusing me a bit that we have the pair composed with the triple.
Yeah, that's this phenomenon. H composed with a pair. You forget about the fact that H is a triple.
Okay.
You always
Yeah.
take seriously the left side. So Alexander, did you follow this, or should we re-explain?
No, it's fine.
So here we then get x plus y comma z, and that needs to be composed with plus. But of course, again, by definition, is the same as x plus y plus z. So we've worked out that this triple composed with that morphism is exactly x plus y plus z, and the same type of argument will give us the same thing for the bottom one. So if at the top they're equal, at the bottom there will be equal as well, for any c and any x, y, z. So we've proved our claim that we don't have to require this for all generalized elements. We can just require for a specific one, namely for x, y, z being pi1, pi2, pi3. And then in that case, it's the equality of these three maps. But what is pi1 plus pi2? We can simplify further. What is pi1 plus pi2? Can we simplify further? Yeah, we could. So let's write down what pi1 plus pi2 is. That's no, okay, sorry, no, we can't simplify. We can't simplify it further, but we can still draw this out as a commutative diagram. So from R cubed, we go to R squared. Cross R. By considering the morphism into this coordinate, we consider the morphism pi1, pi2. And into that coordinate, we consider pi3. Then we compose this. This needs to be plus, right? We compose this with plus cross identity R. We will get into R cross R. And then we further compose it with plus. So this triple composite is decomposition of the top arrow there. The bottom arrow has a similar decomposition, where we could go to R cross R squared. Then from there, take identity of R cross pi2, pi3. Again to R squared. And then take a plus. Where here, this map will be pi1, pi2, pi3. But the thing is that these two morphisms are isomorphisms in any category. In the category of sets, it's easy to see. It's triples, and these are also triples, but arranged, represented in a different way. And so you actually have a direct isomorphism between them, and you could actually even think of it as one object, and think of so instead of going this way, you just do that. You skip that middle part, and doing that is exactly doing pi1 plus pi2 comma pi3, and pi1, pi2 comma pi2 plus pi3. But what people usually do is, okay, sorry, there is something wrong here. This is incorrect. I should have written plus there, just like I did there. So what people usually do is they think of this as almost being identity, and they label that arrow with this notation. And they label this arrow with that notation. And then it becomes a nice, sweet commutative diagram with a bit of cheating of notation, which does this. Plus cross identity, going to...
Is that cross the cross from the actual like product?
Yes, we haven't talked about this cross, and we will actually do that now. Identity cross plus. I would imagine, Alexander, this is the diagram you've seen, right?
Yep, that was it.
Yes, and maybe the reason why you didn't quite understand it is because there's a bit of cheating going on in this diagram, as I explained here. Did you understand this one?
Yep, that one was clear.
Okay, wonderful. So now let's explain, because we actually never properly worked out what cross means. But before we work that out, I want to finish off discussion of topological groups. So subject to understanding what cross means, you see now that the associativity axiom has been expressed as a commutative diagram in the category of topological spaces. And we could do exactly with same techniques, we could express identity law and the inverse law with commutative diagrams in the category of topological spaces. Do you believe that?
Would it be like a square down here as well? Or
What should I do? Sorry?
shouldn't it be like a square here?
Yes, it should be. Thank you.
Okay.
So are you happy with the fact that we are going to be able to express other two axioms as well as commutative diagrams? Or should we go into details there?
No, I'm happy.
I'm still going to draw these diagrams. So for the inverse law, I begin with a single R. I go to R squared by taking a morphism induced by identity and minus. So in one coordinate I fix, the other I reverse. Then I add them, and I should get 0, which means the same. It should be the same morphism as going into the terminal object, because that's what singletons are in the general category. Empty product is the terminal object. And then using the structure of the group, the 0 element, which now becomes 0 morphism from this terminal object to R. So then this is the commutativity of this is the inverse law. And for identity law, I could draw a similar diagram. Let me squeeze it in right here. So I skipped the path through generalized elements. I wrote the final answer directly. And then for identity law, we'll have from R, we could go, there is another potential cheating that could be involved here. So we could go from R to R cross R to the power 0. You think of R to the power 0 as 1. So there's an isomorphism between any object and that object Cartesian product with terminal object. And then from here, you go to R squared by taking, you fix the first one, and in the second coordinate, this will actually be cross. Well, yeah, maybe I could have done it in an easier way without having to introduce that intermediate step. So I could go to R squared by identity morphism, and we can call this composite something. We can call this composite 0 dot. It's not quite 0. 0 is this domain, but 0 dot here could be that. And then I could use 0 dot here. So that would be from R to R. And that composed with plus, I want to be identity morphism. This is one side unit law, and the other side will be symmetric, which actually is a consequence from the other axioms. But yeah, Brandon, are you also happy with this?
Yes, I am.
Can I ask, in the specific case of abelian groups, all three of those will be morphisms in group, well, in that category.
Okay, now Carlyle is asking a very interesting question. Before formulating this question, let's summarize the answer to the first one. So what we've done as a result, as a result of below, we can now construct what is called the category of internal groups inside a category. The category of internal groups in any category C having finite powers. We only needed finite powers. If you see here, all the products we used were just powers. When C equals stop, we get the category of topological groups. So internal groups in the category of topological spaces equals the category of topological groups. We have said nothing about morphisms, but it's not difficult to see that morphisms will also be defined by commutative diagrams that express preservation of the operations. Okay, so two things we want to do now. One is to, well, actually, both of them are to answer Carlisle's question. So his first question was, what does it mean to take one morphism cross another morphism? We never properly introduced this in our lectures. And second question, I think, was, what happens if here, instead of topological spaces, we put the category of groups?
No, that's not.
What were you asking?
Yeah, I was just asking if we look at that original symmetric construction.
Yeah.
Right. And instead of group, we take abelian groups.
Oh, but then we just add one more commutative diagram.
Yeah, but then all three those morphisms, plus, minus, and zero,
Yeah.
are group morphisms.
Yeah.
So if we just force them to be topological and group morphisms, then we get that they must be continuous. So does that symmetric construction not take us topological groups?
Why must it be continuous if it's a group?
No, if we do this thing where we force the underlying sets and the morphisms to coincide.
Yeah.
Then
You mean the pullback construction?
Yeah.
Okay, let's go back. Let's go back to the pullback construction.
Because if I'm understanding correctly, the morphisms in that pullback are those that are morphisms in both.
Yes.
So but in abelian groups, that addition minus and zero will be morphisms.
But how will they become continuous? Yeah, but how will you get? What was the problem? The problem was with how will you get the plus to be continuous?
Is that plus not a morphism of groups?
Yes, it's a morphism of groups, but why is it continuous?
Well, if you force it to be if you make them coincide, then the only ones that survive are those that are continuous as well.
Make what coincide?
The function of the morphisms.
Which morphisms?
So in this new category, right?
Yeah.
You will have R squared and you will have R.
But the plus that comes from a single object.
Yeah.
How will I be able to extract that plus and see it as an arrow from R squared to R? This is now an abstract category.
Over an abstract, okay.
An object.
Okay, but I mean just in this specific case, not for
just in this specific case, what you're saying is the same as what we already did.
Okay.
If you want to extract it, if you want to describe it in the language of the pullback, then you should only use the language of the pullback and not use any additional information that you have.
Okay, I'll ask afterwards as well.
Okay. So the problem doesn't get easier with abelianness, but what I thought you were asking was.
I was wondering that earlier as well.
Yeah. So what happens if we take internal groups in the category of groups themselves? That's an interesting question. Now, when we define internal categories, I gave this assignment. I said, describe what internal categories are in the category of vector spaces, and I said it's going to take a long time to do that. The thing is that groups can be seen as special kinds of categories. You take a one-object category, and you require every morphism to be an isomorphism. Then you get a group. And in the same way, you can view an internal group as a special kind of an internal category. So everything we did today about internal groups is actually a special case of what we did with internal categories. And so the question of what happens if I put C to be abelian groups now becomes similar to the question of what happens if C is vector spaces, because abelian groups can be seen as Z modules, modules over Z. And a module over a ring is just a very basic abstraction of a vector space where instead of field, we've got a ring. But let's first answer the first question about the Cartesian product of arrows. For that, I'm going to Actually, I can fit that answer here on this board. We might have touched on this at one of the lectures, but it was very brief. So if I have to, and I'm going to answer this question only for binary case. If I've got two sets of objects, pairs of objects rather, x, y, a, b, I've got a morphism from a to x, f, and I've got a morphism from b to y, g. And let's draw in the projections as well, pi 1, pi 2. This is for the first product. For the second product, we very often use the same pi 1 and pi 2, although of course they're different morphisms. So if I want to be very formal, then I have to call them something else. I could, for instance, call them pi 1 prime and pi 2 prime. F cross G is defined something that fits in this diagram. But how can we make something fit in this diagram? Well, I can compose these two. I'm going to get an arrow into x, which will be f composed with pi 1. I can compose those two. I'm going to get an arrow into y, which will be g composed with pi 2. And then I simply define f cross g as the arrow that's induced by f pi 1, g pi 2. So this is the unique arrow that makes these two triangles commutative, 1 and 2. When we learn linear algebra, we learn how to multiply matrices. So there's some kind of linear algebra to learn here, how to compose these kinds of morphisms. And we already established one rule, namely that UV composed with W equals UW composed with VW. This is one rule for linear algebra of composition in a general category. Another rule would be F cross G composed with F1 cross G1, F prime cross G prime. Actually is the same as F composed with F prime cross G composed with G prime. And you can continue on deriving some useful formulas like this, which will be useful for calculations later on, like some of this was in the other case. So that answers the first question. I think intuitively it's also quite clear. We can wait for you. Intuitively, it's also quite clear what f cross g does, because kind of fx on the first argument, a and g on the second. So f cross g will take information from a and transfer to x, and from b to y, and because we had a pair, we end up with a pair. Well, while Carlisle comes back, do you have any questions, Alexander and Brennan?
Nope.
Nothing from my side.
By the way, talking about linear algebra, I think we did talk about this right at the start, if I'm not mistaken, but I could be wrong. It becomes interesting to investigate what are errors from a co-product to a product. What if on one side I had a co-product? So what if I replace one side with a co-product instead of product? And I now have an arrow from here to here. How can I describe it in terms of arrows from A, B to XY? Can I? This is a morphism going into product, so it decomposes into a pair, right? But now each of these are morphisms going out of the co-product. So they also decompose into a different kind of pair.
Sorry, say that again.
This morphism is a morphism out of co-product. So it also is given by two composites, this one and that one. But now that will be a kind of different pair. We shouldn't use the same notation. So one uses vertical notation for one and horizontal for the other, so that in the end, the middle one ends up being a matrix. So if I relabel my things to make the matrix more apparent, I can call these ones A1, A2, and this I can call X1 and X2. And the composite of this map with iota 1, which will be mapped from A1 to X1, I can call that small a11. The composite of iota 2 with that map, I can call that small a21. Then this map here, I've got another map going there, right? That's the composite of iota 1 with that map. So that map I can call so I'm keeping the indices according to the domain and codomain. So 1, 2, 2, 1, 1, 2. Sorry, that was 2. Yeah. 1, 2, and this one will be 2, 2. And now this map here is okay, when we talk about coproducts and products simultaneously, it's more convenient to write the pairs we've been writing horizontally, to write them vertically, so that we are coherent with the notation in linear algebra. So I'm going to no longer write a morphism going to a product as a horizontal pair, but rather as a vertical one, in other words, like a column matrix. So this one then will be the horizontal one, given by two maps, right? So this map and that map. So it will be A11, A21. This, on the other hand, will be A12, A22. And now these two together induce that one, and they should be vertically tiled. So this one will be A11, A21, and but the bottom will have the pair A12, A22. But now, when describing this morphism, I first thought of it as morphism into the product, and then each of them as morphism out of the coproduct. I could have also done it the other way around. I could have thought of this as morphism out of the coproduct and then considered this composite instead. If I had done that, that would have given me a different decomposition, namely A11, A12 as a column, and A21, A22 as a column as well. And it turns out that we can prove that these two are equal. And that's why when we write a matrix, we don't indicate whether we read rows first or we read columns first, because it doesn't matter. It's actually a theorem of category theory that tells us it doesn't matter. But we will come back to this another time. This was just to give a synopsis of how one can develop this linear algebra calculus a bit further by actually introducing matrices. I want to now touch on the second question. Since we now define internal groups in an abstract category, it would be meaningful to check out what they are in some other categories that are not the category of topological spaces.
So I have a question, actually.
Yes.
So right now we have defined a category of internal groups.
Yes.
Something alike. But usually, as I have seen, so for example, in case of topological groups, it starts some group, and we try to find some topology that suits it. So
Yes.
is there some general way of constructing topological objects, like we construct group objects?
So that's the question that I said it's an open question. We don't know what is a nice way to do that. There is a way to do it It doesn't quite give us topological groups though. There is a way to internalize topology inside a category, but it is not capable of capturing topological groups. It's capable of capturing maybe other things.
Yeah, because I found it very, yeah, because in book there was like some groups from start, and a problem was to find some topology. That's so it's this.
We can still formulate that question categorically, and we can formulate it as follows. Basically, I can go back here to this pullback diagram. Now that we've constructed this top group as internal groups in the category of topological spaces, right? I know I've got insertion into the pullback, which then gives me this functor. Sorry. Yeah. So, but now this functor here we have only when this is actual topological groups, right? For if instead of top I had an abstract category, I wouldn't know how to make a group out of it unless I fix my base of generalized elements, then I can turn it into a group. And so that question that you're asking, I have a fixed group G, and I want to find a topology on it, is basically describing which objects from this category map to there. Now this functor itself turns out to have very nice properties, which is called the topological functor. It has similarly nice properties as this functor does. This is also a topological functor. And just to mention, University of Cape Town was one of the worldwide centers for investigation of topological functors. Interestingly, I found some new applications of topological functors in algebra, which was an interesting coincidence of me being in here, and but that's a separate story. So the question you're asking, Alexander, can still be stated categorically, but it cannot be generalized to the case where you stop with an abstract category. Does that make sense?
Yeah, it does.
We now move to make one more move now to explain, to investigate what are internal groups in the category of groups.
So with category of groups, you mean like one dot objects with morphisms, or regular category of groups?
Regular category, usual, no, not one dot object, no, just the usual category of groups.
Yeah, all right.
But okay, so first of all, let's state the obvious things. The first obvious thing that we already worked out is that internal groups in the category of topological spaces are exactly topological groups. Second thing is that internal groups in the category of sets are the usual groups. This is an isomorphism. Well, not really. I mean, depending on how we define internal group, if the product is fixed or not. Think of it as equality as well. But what about other categories? And what we're going to do now is to look at what are internal groups in the category of groups. So we've got a group G, which has its own plus, right? But then there is another plus, the one that goes from Cartesian product of this group with itself into called plus prime. Yeah? And we know that plus is associative and it's a group structure. By making use of generalized elements, we can also eventually conclude that plus prime is going to be group structure 2. So we have two group structures, but what's special about them is that one is a homomorphism of the other. Let's write down what this means. If I take a pair AB here, right? So take a pair, I add them in the Cartesian product, and then I apply plus prime. That should be the same as first applying plus prime to each of them, and then adding them. This should be a different pair, sorry, maybe I'll call it CD. I'm just writing down what it means for something to be a homomorphism. But of course, we can rewrite it in a nicer way if I use usual notation for plus prime. So first of all, the pairs get added component-wise. So it will be A plus C, B plus D. Plus prime is applied to that, right? I can rewrite this as A plus prime B, and then C plus prime D. And here I could write this as A plus C plus prime B plus D. Eventually I get this formula, which now you see is actually a symmetric formula in terms of plus and plus prime. This is called the interchange law. So it turns out that an internal group in the category of groups is basically, I mean, I did skip a few steps here. If I hadn't, then we wouldn't be able to finish this lecture. But anyone can try to complete those steps. I mean, how to get to this point from the diagrams to all this. But it seems like we're saying that an internal group in the category of groups is a set together with two group structures satisfying the interchange law. So the plus is a group structure, plus prime is a group structure. So G with plus is a group, G with plus prime is a group, and then interchange law holds. Well, interchange law only guarantees that plus prime is a homomorphism. We also want to know that minus prime is a homomorphism, right? But it will turn out that that follows from the fact that plus prime is a homomorphism. What plus prime is going to do, oh, sorry, one important thing. These two group structures share the same zero. Why? 0 prime is a morphism from G to the power 0, well, rather G plus to the power 0 to G plus. But what is G plus to the power 0? That's the eternal object in the category of groups. It's a singleton group having just 0 in its element. So 0 prime selects an element in G, but this must be a group homomorphism, right? But I wasn't quite correct to say what I said here, I think. 0 prime must be a group homomorphism, therefore it must map this to the 0 of G. And so it forces 0 and 0 prime to be the same. So these two group structures share the same 0. Maybe I can get away with minus, talking about minus. I think this is now sufficient to come to the conclusion that I want to come to. You've got interchange law, two groups having the same 0. By cleverly substituting zeros in the interchange law, you will get very powerful conclusion. So who can see a clever substitution of zeros in the interchange law to give us a powerful conclusion?
C and D0.
Here is the interchange law. So Carlyle says let's take this one and that one to be 0. What are we going to get? Yeah. If these two are 0, C and D, then here we'll have A plus 0, which is A, 0 plus D, which is D, So we'll have A plus prime D. On the other side, we'll have A plus D. Do you see that, Alexander and Brennan?
Yeah.
So these requirements force class and class prime to be the same. Okay. So actually, we don't have two group structures. So let's now revise. We have one group structure.
So does it do like nothing at all?
Let's see. We still have the interchange law, right? So we shouldn't forget about that. We have one group structure which satisfies the interchange law. And now, can you think of other clever substitutions which will derive a simplification of what the interchange law actually says? I think I made a mistake here, right? CB, yeah, I did, sorry.
If you make A and D 0.
Right. So if we take now A and D to be 0, put these ones to be 0.
Oh, that's cool.
We get commutativity. Yeah. But if we had commutativity, we also have associativity, right? Then the interchange law would hold, wouldn't it? It's just rearranging the terms, the interchange law for one operation. So this interchange law becomes equivalent to the fact that we've got an abelian group. So the answer to our original problem still needs to be, detail still needs to be proved because we did a lot of skipping. But otherwise, the answer is that internal groups in the category of groups is a category of abelian groups. And that's quite surprising because in all the other cases, this was an extra structure. For a single, like you were asking, Alexander, you can take a single group and ask how many topologies you can put on it so it becomes a topological group. So you can have several, right? Also the other way around. So you can take a single topological space, you can have several group structures on it, making it a topological group. Same set, several group structures making it into a group. But for internal groups in the category of groups, you can't do that. There's always one because the two classes end up being the same.
So there's like exactly one structure, one group structure groups. Yeah?
Yes. For every group, there is at most one internal group structure on it, and it exists if and only if the group is abelian.
Oh.
Internal groups in the category of monoids. You see, we didn't make use of inverses here. Internal groups in the category of monoids is still the same as the category of abelian groups. In fact, you can even do more than that. You could take internal groups in the category of magmas. What is a magma? It's a set with a constant and the binary operation, where you only require that x plus 0 is x and is 0 plus x. Only that will turn out to be sufficient to get that this is the category of abelian groups.
What happens if you take a group of semigroup?
If you take internal group in the category of semigroups, that's a good question. I don't know the answer, but I can guess that it will still be abelian groups, but it has to be checked.
You don't have 0, so.
Yeah, I know. Yeah, but it will still be for the semigroup, I think.
Because you get some kind of 0.
No, I'm not sure. I don't. Yeah. So actually, I cannot be 100% certain. It might be that when I'll upload this video, I'll say, "Oh, but this was so obvious," but maybe not. I don't know.
So in magma, like we don't have a defined every sum wanted to cause any problems.
Sorry, say it again.
So as far as I remember, in magma, we don't have like defined every let's say product. or
No, the definition of magma I'm using here, class is defined for any two pairs.
it's pseudo magma. Yeah.
I mean, any two elements, so it's defined for any
Okay.
pair.
Yeah. So like complete our object to some abelian object, abelian group.
Well, I mean, we can try to work it out, right? You mean are you asking again for semigroups?
No, I was talking about magmas actually.
Yeah, so for magmas, you really get it's the same as abelian group. So this magma will turn out, this plus of the magma will turn out to be the same as the group plus, and it will turn out to be a commutative. We only used associativity after we reduced the two operations into one. And to reduce the two operations into one, we just used 0 here. We didn't use associativity. So that's the proof will be actually the same here. Yeah, for semigroups, it's an interesting question. I'm not doubting myself. I'm doubting this guess. So if in this equation you interchange law, right? If I take so it's the plus that doesn't have 0 anymore. Yeah. So the best I will get here will be that a plus 0 plus prime 0 plus d equals a plus d, right? And then I could put another 0 there. I could put d to be 0 as well. Why would I want to do that? No, I don't know why I want to do that.
I wonder if you'd be able to conclude somehow that 0 plus normal plus 0 is 0.
So what if my plus was for any x and y, x plus y is my fixed element. So what happens in the case when x plus y is a fixed element c, constant c? This is associative.
But then you also need c to be with plus.
Yeah, c plus c will be c as well. Yeah. So what happens in that case? In that case, the interchange law becomes c plus prime c. So this will be c, that will be c, that fixed c, and maybe I can call it c bar, distinguish it from the other one. So I'm taking a semigroup where I want to analyze the general interchange law first.
Yeah.
So I'm taking the case where my semigroup structure is such that for any two elements x and y, x plus y is fixed c bar. Then this is going to be that c bar. That's going to be that c bar as well, right? So we'll have here c bar plus prime c bar.
Then c bar must be 0.
What do we have here on the other side? On the other side, we have c bar.
Yeah.
So then c bar ends up being 0. And I think this means that it's not necessarily a abelian group. Now I have an ordinary group. So I was completely wrong there. This is not true. Counterexample. Take a semigroup where class is a constant function. Then internal group in there will be whatever that constant value is a group structure where that value is identity element. Is that true? So plus prime will be homomorphism. What about minus? Minus will also be homomorphism because minus 0 is 0. Yeah. I'm still taking a risk here, but now I feel that this should be correct, but the other one shouldn't. What do you think, Alexander? Do you agree with my conclusion?
Yeah, constant example seems reasonable.
Yeah. It's interesting because, I mean, every set can be seen as a semigroup in a very strange way. I mean, any pointed set, basically. So that's another way to think about it. So I could think of the category of pointed sets, which is denoted like this, to be living inside the category of semigroups. And so the category of groups inside pointed sets will live inside the category of semigroups. But this category is the same as the category of groups. The base point will just be the identity element. Great.
Oh, that's really weird.
Sorry?
That's really strange, I mean.
Yeah, semigroups are quite very, very subtle structures. They're really, they shouldn't be called semigroups. Maybe they should have called quarter groups or something. Very far from groups.
Yeah.